Welcome to a brief introduction into control theory, a ubiquitous subject because everything that is human-made and surrounds us is being run by control algorithms. Control theory can be considered as a key to transform the objective reality. Control theory is, in its essence, about two entities. There's something that controls and something that is being controlled. The first one is usually called controller or agent, while the second one is usually called controlled object, a system, a plant, environment, or something else depending on the context. As such, these two concepts are fairly general. A controller might be, let's say, a living being or its brain. It can be a computer or it can be a microcontroller, and actually anything that produces what's called control actions. Whereas the controlled object does not even need to be a physical entity. It might as well be a virtual one. For example, a video game, a stock market. Physical examples are easy to come up with. Give me a robot, a vehicle, plane, appliance, it can be biological system. Pretty much anything that has designated state and can be influenced by control actions, in other words, manipulated. Formally, systems can be described as follows. First of all, we need some notation. So let us denote the internal state by X, control input, control action, by U, and output by Y. A general form of a system goes as follows. Next state of the system is a function of the current state and control. Output of the system is some other function of the current state and possibly input, which is actually not so commonly the case. Probably the simplest form of a system is the so-called discrete time system. This is a system in which time is treated as a sequence of discrete moments. In such a case, we simply put some index, let's call it k, which is an element of natural numbers with 0, for this notation next quote-unquote current over here, and we put index for the state, for the input, and for the output, and here is the description that we get. And in general, the state, the input, the output are vectors of some dimensions. Let's give some examples of discrete time systems. Speaking of video games, this could be something turn-based, for example, such as chess or Go. And in chess, you can consider the state, for example, to be essentially the stateful, these squares on the board arranged in a vector. So, for example, this could be something like the first position, which corresponds to a1, a rook, pawn on a position that corresponds to a2, nothing on a3, and so on and so forth. But there are, of course, other ways to arrange this, and input could be, for example, pair of squares, which corresponds to a move. Another example could be a digital electronic device with a determinate clock rate, such as a microprocessor, in which case we can consider the state to be just the current state of all the registers, and input just a command. Finally, let's say a stock market where an investor makes just one transaction per a trading session, which could be, for example, a day. And here we can include his or her total assets into the state vector as well as the stock price and so on and so forth. And the input could be buy or sell stocks. But the most important category of systems is perhaps the time continuous ones. These are usually described by differential equations. And practically any physical object is a continuous time system. So let's consider, for example, a mobile-wheeled robot. This is a system which is described by 5 differential equations depicted over here. We have our two coordinates on the plane. This is chi and this is eta, and I deliberately did not use x and y in order not to confuse with the state and output. V is the speed, alpha is the angle in the global coordinate system, omega is the revolution speed around the vertical axis. So the first three equations are basically kinematic. We have our chi component of the speed, which is just the magnitude of the speed times the cosine of the turn angle, eta the same times the sine, and derivative of alpha the turn angle is exactly the revolution speed. These two equations for v dot and omega dot, they are derived simply from the second Newton's law. And for the input, we just take the force, the pulling force acting on the robot, and turning torque, M. Our picture of systems wouldn't be complete without mentioning what's called stochastic systems, systems with randomness. So for example, in the discrete time case, instead of a determinate value for the next state, given the current one and the control input, we would only have probability of taking a certain value, and given not just the current state and the current action in general, but the whole history of preceding controls and states. In the continuous time case, it gets to a rather complex object called stochastic differential equation, whose more or less generic form is depicted over here. And without going too much into detail, let's just compare the description over here in the deterministic case and stochastic case. What we see is that there is an additional term that has to do with the random walk. So precisely this diffusion term over here is responsible for randomness in the system. Let's give some examples. So for instance, in the case of turn-based video games, if we add a random number generator, we would get a system that falls into this category nicely. Or a card game, such as poker, let's say. In the continuous time setting, an example could be an investment portfolio where we consider development of the prices, stock prices continuously, and we can trade throughout the trading session. Otherwise, virtually any physical object with random noise can be considered within this category over here. Speaking of control goals, several options are possible. Just a few of them are listed here. This could be something as simple as reach a desired state, for example, park a mobile robot. Something more sophisticated as stabilization, which is like reaching a desired state but also keeping it. So you could think of an inverted pendulum that we need to upswing and hold in vertical position. Something yet more sophisticated is so-called optimal control, where we are optimizing some performance mark. For example, in case of investment portfolio, we might be interested in maximization of total assets by wisely trading on the stock market. And then there is identification, which is actually an extremely important part of control theory. Identification is about estimating the state of the object from the output. So the output can represent, for example, measurement data from sensors. And from this measurement data, we want to determine what is happening inside of the object. Let's talk about control methods by which we can achieve the state control goals. And first of them will be the so-called proportional integral derivative controller, or PID for short. This is probably the most popular control method out there. Its roots can be traced back to as early as 19th century. For example, the so-called centrifugal governor, depicted over here for controlling engine speed, could be understood as a mechanical representation of a PID controller. Let's consider the following example. we have a system that is described by a linear differential equation, and let's say that both the state and the input are just scalars, and our goal is to stabilize the system, i.e. to drive the state to zero. We take just the proportional part for the controller. This reads U equals minus what's called control gain, K, times X times the state. And if we plug this in into the system description, we get a closed loop of this form. Now the coefficient in front of X in the right hand side description of the closed loop is now A minus K, and if we set K to be greater than A, then for any initial condition X will tend to 0. A full description of PID for a system with an output and non-trivial set point y star reads as follows. We have proportional term, integral term, and derivative term. The intuition behind this as follows. If the arrow, which is y minus y star, is large, then the control action becomes larger. With these two, the effect is the same, except that over here we have a cumulative effect over the past error. And here we're sort of anticipating the development of the arrow while looking at the derivative. Next control method is the standard one, quote unquote, for optimal control. This is called Model-predictive controller. Model-predictive controller, or MPC for short, is about predicting future sequences of states under sequences of control actions and finding the optimal one with respect to a metric called stage cost. Stage cost can be understood as a quality index of a state and control action. We take those and sum them up to some step n, which is the horizon. So we look some n steps ahead and we minimize over the actions that generate the respective states and subsequently stage costs. And this is all done under state prediction. And state prediction is performed via the model. Now this is precisely description of a discrete time system that we are MPC controlling. The algorithm goes as follows. We take the system specification, i.e. model, i.e. function f, the right hand side, horizon n, stage cost, and for each time step with index k, we solve the respective optimization problem, the K MPC problem. A solution of this problem is a sequence of optimal control actions. Off of this sequence, we take the first element and feed it into the system. In the next step, we repeat the whole process. In practical applications, there are usually physical and safety-related constraints. This can be nicely integrated into MPC. We simply require every state over the prediction horizon to lie within the specified constraint, and the same applies for the control action. So capital X and capital U simply represent constraints, respectively the state and input constraint. What you see here is an application of a model predictive controller for a mobile robot parking problem. The mobile robot starts at the square marked in the center and travels to the bottom right corner while also achieving a desired orientation. Next popular control method is the so-called sliding mode controller, or SMC. This is a kind of a controller with switched structure. Switching happens on different sides of the so-called sliding surface. Under SMC, the system enters special mode called sliding mode, which is exactly on the sliding surface, and then it slides along the surface straight to the origin, and so the stabilization is achieved. Here is a little example of sliding mode control application. We have a two-dimensional system and a sliding surface which is described by x1 plus x2 equals 0. If we pick such a controller, we get finite time convergence to the sliding surface, and once we are on the sliding surface, the overall system amounts to this simple one-dimensional one because of the relation x2 equals minus x1, and we get the convergence of x1 to 0 and respectively x2 to 0, and so stabilization is secured. Sliding mode controller is, for example, used in some traction control systems and anti-block systems. Traction control is especially important in off-road vehicles, where too high slip can lead to excessive tire wear and fuel consumption. There are actually a lot of types of control with different level of complexity and different features. For example, so-called robust control is the one that maintains functionality despite presence of uncertainty, such as, say, noise, measurement noise, actuator noise. Adaptive control is the one that contains learning elements that adapt to the changing environment. Fault-tolerant control retains functionality in presence of faults. Certain types of systems, for example network, complex or hybrid, in turn require certain adaptation of the control algorithms applied. This is where formal analysis of control systems is required. Control algorithms have to be formally certified for their functionality. There are various tools for that sake, but probably the alpha and omega of those is due to Lyapunov and via the so-called Lyapunov functions, which play the role of abstract energy functions analogous to mechanical or electric energy, let's say. In a nutshell, what Lyapunov theory says is that if there is such an abstract energy function that has certain properties, in particular it is positive definite, it depends on the system state, and if the derivative of this function is negative, then the state necessarily converges to an equilibrium. Let's recall the example from the sliding mode section. So this is the system, this is the sliding surface, and this is the controller. Pick an energy function in this form, absolute value of x1 plus x2. Differentiate it, unwrap all the terms, and observe that the derivative is not greater than minus k, which is a constant, which means that x1 plus x2 necessarily converges to 0 and moreover in finite time. As for the task of identification, i.e. determining the system state from the output, there are so-called observers. They could be roughly understood as virtual sensors, algorithms that are physically not there but are capable of measuring quote-unquote hidden states. There are of different types. Some of them are listed here. Probably one of the most popular ones is the famous Kalman filter. Let us conclude this video by saying that control engineering nowadays is as relevant as it could ever be, despite already being a classical discipline with almost 100-year history. The area where control engineering and machine learning, the backbone of artificial intelligence, meet is so-called reinforcement learning. This can be thought of as being a kind of an adaptive controller. It turns out that only synergy of the two disciplines can enable guarantees on reinforcement learning, which is extremely important in industrial applications such as self-driving cars, autopilots, complex robots, etc. With that being said, thank you all for listening. Good luck studying control theory and hopefully making it to reinforcement learning and other AI relevant applications.